So in the nuclear fission, we get the uranium atom split into barium and krypton. Where does the energy come from? Well, if we look at the mass of the reactants, so this is the mass of the nucleus for uranium-235. Here's the mass of one neutron. We get a total of 236.05258 atomic mass units. Our products, barium-56, krypton-36, and 3 neutrons, the sum of their masses is 235.86769 atomic mass units. This is not a difference in the last significant figure, the uncertain digit. This is a difference over here. So it is a small mass difference, but it's significant. Because what's happening here is that matter that was lost was turned into energy. So this is the part of nuclear happenings where energy is not conserved and mass is not conserved, right? Because mass can be turned into energy and vice versa. Oh my goodness. So here is Einstein's famous equation, E equals mc squared. E is the energy produced, m is the mass that is lost, and c is the speed of light, but squared. Okay, so we're going to calculate the energy produced in the fission of uranium-235. So we're going to go back here, and we're going to find our mass difference, 235.86769 minus 236. Oh, I'm doing it backwards, but I'll just change the sign. So 0.18489. Atomic mass units. So what is C?
2.10 times 10 to the power of 8.
Okay, we'll go with that. 2.998 times 10 to the 8 meters per second. So if we do this mass times the speed of light squared, we're going to end up with atomic mass unit meters squared per second squared. That doesn't sound like an energy unit, does it? A joule is a kilogram meter squared per second squared. So we need to convert atomic mass unit into kilograms. So atomic mass unit related to grams, and then go from grams to kilograms. Well, this one should be easy. Kilo means 10 to the third, right? So 1 kilogram is 1 times 10 to the third grams. How many grams how many atomic mass units in a gram? What's the definition of atomic mass unit? It's the mass of a carbon-12 atom is exactly 12 atomic mass units. And how much does a mole of carbon-12 weigh? 12 grams. So I need Avogadro's number in here. One carbon-12 equals 12 atomic mass units. 1 mole of carbon-12 equals 12 grams.
So the mass of uranium times that conversion.
So we could do it this way. 1 carbon-12 atom is exactly 12 atomic mass units. I'm sure there's a more elegant way, but this is all my brain's capable of. And a mole, 6.022 times 10 to the 23rd carbon-12 atoms would weigh 12 grams. And if I screwed up, please feel free to tell me because, yeah. So, divide by 12 times 12 divided by 6.022 e to the 23rd divided by 3.0702. Let's stick that over here. Times 10 to the minus 28 kilograms. Of course, you know, the day I need my decent calculator, I left it at home on the couch. Make sure I understand how this one's working. No, this minus sign is kind of important. Did anybody else get that number? Because I've screwed up twice now. Okay, I'll do it again.
Yeah, I got 45.
Oh, wait, that is.
Oh, there's been negative on top.
There you go. No, that's correct. I saw it.
Yep, got it.
Yeah, okay. So that's kilograms, meters squared per second squared, which is equal to joules. So this is the sort of problem that we should be able to do, even though we're not shown how to do it, right? We can find some information, we can convert some units and put things together. This is an example of how the base units in the SI system work together. Kilogram is the base unit of mass, not gram, because The definition of a Newton and a joule all involve kilograms. So is that a lot of energy? 10 to the minus 11 joules? No, it's not very much at all. But in a measurable amount, in a visible amount of uranium, how many atoms are there? A lot, right? I mean, if we multiplied this by Avogadro's number to get a mole, it would be 1.66 times 10 to the 13th joules, which granted would be 235 grams of uranium-235, but you could hold that, right? So let's look at a helium-4 nucleus and look at what we know to be in it. There are 2 protons, so 2 times the mass of the proton, and 2 neutrons. So here's the mass of 2 neutrons. And so the total of that is 4.03298 atomic mass units. But the actual mass of the helium-4 nucleus is 4.00260 atomic mass units. It's less. This is called the mass defect. All stable nuclei have a mass defect. Their actual mass is less than the sum of their parts. So, where did that mass go? That mass went into energy, and that is called the nuclear binding energy, which is defined as the amount of energy required to break apart a nucleus into its component nucleons, into protons and neutrons. So nuclear physicists often use a different unit to report energy, the electron volt. And this is one way I know that the Chem 1A students are Googling answers to the question about the energy transitions in a hydrogen atom, because they're giving me answers in electron volts. This is the first place in our book and in our classes that we talk about electron volts. I'm like, dude, zero.
Just really smart, you know?
Oh my goodness. So an electron volt is the kinetic energy of an electron accelerated through a potential difference of 1 volt. So a mega electron volt, capital M mega prefix, is 1.6 times 10 to the minus 13 joules. Right? So a very small amount. But if you look at the relationship between one atomic mass unit of of mass that's lost and turned into energy using E equals mc squared, you would come up with the equivalent of 931.5 mega electron volts. It's still a small amount. So this is a conversion factor that you can use when doing problems. Some of the problems might ask you to answer in joules, and so you could go through what we did in the previous example of mc squared and converting atomic mass units to kilograms and blah, blah, blah. Or you can just use this, atomic mass units to mega electron volts, and then if you need joules, well, here you go right here. Okay?
I'll try to.
And these are not numbers that I expect you to memorize,
Yeah.
right? If you're a nuclear physicist, you should memorize those, but none of us are nuclear physicists.
You never know.
It's true. You never know. My husband just found out that one of his students was part of the team working on the project that got the Nobel Prize, the Nobel Prize in Chemistry in 2021. Last year. You know what I mean. So, yeah. A guy from Fresno City College.
What did they get the prize for?
It's not something I could, well, first of all, it's not something I actually remember. It's also not something I could tell you about in like a couple minutes. It's kind of complicated. Okay, calculate the mass defect and nuclear binding energy per nucleon for uranium-238, which has a mass of 238.050784. Oh, I skipped one. Let's do this one first. So the mass defect for helium-4 is 0.03038 atomic mass units. What's the nuclear binding energy? So there's the number I keep forgetting, 931.5. So we can just convert atomic mass units to mega electron volts. Much easier than involving the speed of light. $28.29897, 28.30 mega electron volts. Well, this is asking what's the nuclear binding energy, and it doesn't specify the unit. So I think this is easier. If it wanted it in joules, we just used another conversion factor. So we often look at the binding energy per nucleon. What's a nucleon?
Collective term for protons and neutrons.
Collective term for protons and neutrons. It's the particles in the nucleus, the major particles in the nucleus, because there's other things we can talk about. So per nucleon means you're going to take the binding energy for that nuclide and divide it by the number of nucleons, which happens to be the mass number, right? And then you can compare different nuclides, and if you have a larger binding energy per nucleon, it's more stable than it has if it has a smaller one. Okay. Calculate this mass defect. So this is wanting us to calculate binding energy per nucleon in mega electron volts. So here we've got the mass of the atom. So the uranium-238 is 238. Gosh, darn it. 0.050784 atomic mass units. And how do we figure out the mass defect? We need to subtract, but what are we going to subtract? 2?
38 for.
Well, these are the same number.
Oh.
These are the same.
Yeah, that one from the 238.
No,
No.
we have to calculate the expected mass. So we need to know how many neutrons, how many protons, what do they weigh, and put them together. So uranium-238, uranium is element 92, right? So 238 minus 92 is 146. So we have 146 neutrons and 92 protons. So this is another thing I don't remember, which is the masses of the protons and neutrons. So they're very similar, and you might, well, they're one. And that's what we would get if we did the mass number, we'd get 238. But we're looking at a very small mass difference, and so we need to be as precise as possible. So the proton 00783, I'm just going to write these on the board. And neutron is 1.00866. So we have 146 neutrons times 1.00866 atomic mass units per one neutron. So 146 times that. So 147.26 and 2, 3, 4, 5, 6. Atomic mass units. So if we used 1, we'd have 146. It's actually 147.26. 92 protons times 1.00783 atomic mass units per proton is 92.7, 2036 atomic mass units. And then when we add those together, we get 239.98472 atomic mass units, which should have 3 decimal places. So this is the expected mass, and that's what we're going to subtract this from. $1.933936 atomic mass units. That's the mass defect. We need to convert that to energy. So 931.5 mega electron volts per 1 atomic mass unit. We're getting 1801 .46 mega electron volts. So that's the total binding energy for the nuclide. But if we want per nucleon, then we're going to take that total amount, 1801 point, can't even mutter things under my breath. Divide by the number of nucleons, which is the mass number of 238. Seven 0.5692. Any questions?
This isn't how the book does it, huh?
It isn't?
I think because I was doing the homework problems for this, and like the way my work is done, it's like a lot different. Yeah. Seems like a little
Well, I
easier.
haven't looked at the book for 3 years, so
Yeah.
it could be. How does the book do?
Gosh dang it, there goes my headphones.
So good for them.
It's broken now. Like the tip, like it does it right on some parts. So basically, I think
It looks the same to me.
I don't know why that like confused me.
Maybe because I wrote lots of things out separately. Because they're just showing 92 times this plus 146 times this is equal to that, which is a lot easier to look at. This is a good place to practice your sig fig skills.
Yeah.
Okay. This is definitely a place where you do not want to round too much. Because when you're looking at small mass differences, precision matters. So the maximum nuclear binding energy per nucleon is at A equals 60. That is neodymium. And so here's a graph of binding energy per nucleon versus mass number. And so we see that these small guys are less stable, and the stability increases here, and then it slowly falls off. So this is the most stable region right here. And things on this side fix their instability by undergoing fission, by splitting. And on this side, they fix their instability by undergoing fusion, which we'll talk about. So breaking heavy nuclei into lighter ones is exothermic, but combining light nuclei into a heavier nucleus is also exothermic.
How does that make any sense?
Because matter is not conserved. Yeah. So when you break the large one into smaller pieces, some matter is converted to energy.
That makes sense.
And when you smash some little ones together and fuse them together, some matter is turned into energy. Yeah. So, nuclear chemistry, all those things we hammered into you, not true anymore. The good news is that the total of mass and energy is conserved.
Yes.
So there's that, but they can go back and forth.